Hello everybody, today we're going to be taking a look at another tree problem. This problem is called finding the diameter of a binary tree. So let's take a look at the problem. Given the root of a binary tree, return the diameter of the tree. The diameter of a binary tree is the length of the longest path between any two nodes in the tree. This path may or may not pass through the root. The length is measured in the number of edges between the nodes. Alright, so how do we approach this problem? Well, first we need to get an understanding of what the problem is actually asking for. So back to the whiteboard. This is a binary tree. As you guys remember, the definition of a binary tree is every node in the tree has at most two nodes that are connected to it. So you see, this is specifically a binary search tree, but it's essentially a binary tree where this tree has a left node and a right node, and each of those nodes have their own left and right nodes. They can have their left and right nodes if they wanted to. So what is the diameter of the tree? Well, going back to the problem, it is the length of the longest path between any two nodes of the tree. So you see how in this, to traverse to 4, for example, you have to go these two edges, so the distance is going to be 2. However, the longest path would be something like this. So we'd go from 4 to 2 to 1 to 3, and that's a diameter of 3. You might also notice that you can also get to 3 using this, starting from 5 to 2 to 1 to 3, but essentially the diameter is going to be 3. So that's essentially what the problem is asking for. Now, how do we go about solving this problem? Well, one thing to take in mind is that essentially, when you're calculating the diameter of a tree, you're essentially taking a look at the longest distance between the left subtree of a root. So it's going to start from a root position. It can be the actual root of the tree, like at the top value, or it could be any other root of the tree. But the diameter is found by basically the height of the left subtree and the height of the right subtree. So we have to find the maximum value of these two combined heights. And if you remember from a previous problem, we've had experience calculating the height of a height of a tree and a height of a subtree, which are essentially the same thing. Essentially, we start with the assumption of we're returning 0. Otherwise, we're going to be returning the height of the maximum value of the left subtree and the right subtree plus 1. Max of left, right plus 1. This is kind of like some not even pseudocode, but it's just an explanation of how you would find the height of the tree. So you'd have something like this. If the root is like none, return 0. Else, you calculate the maximum of the left subtree and the right subtree, whichever subtree is bigger, and then you'd add 1 to it. And you'd call this function recursively. Left and right are the recursive functions, where we're going to recursively call finding the continuous path, continuously recursively calling the left subtree and then the right subtree, find the height of them, and then add the heights together to find the maximum value. So, how would this look like in code? Let's take a look. Sorry about that. Already, I set up the class tree node. So, let's take a look. We're going to say def diameter of binary tree, something like that. And then we can have we'll just say the root as the input. The root is going to be the input, in which we're going to be inputting a root, and then we're going to be returning the final integer. So now we'll start with a variable called max diameter, because this is what we're trying to figure out. We're going to start by assuming it's 0. Next, we're going to put our recursive function in. This one, I'm going to call it DFS, and the reason being is this recursive function is going to be essentially a depth first search. If you guys remember or recall what a depth first search is, essentially we go one by one, starting from the root, going deeper into the deepest branch, then traversing all the way up and back to the original branch. So that's how a depth first search kind of looks like. This is how we're going to do it recursively. So as we remember, if not node, we're going to be returning 0. This is standard for finding the height of a binary tree, because we know that if no node exists, that means there's no tree left to find. We're just going to be returning 0. This could be either if the original root is 0 and there's like no root, or it could be during one of the recursive functions where essentially we basically end the depth first search. We can't go any deeper, and that would return 0 for the initial height. Next, we're going to be calling the left subtree and the right subtree recursively, and to do this we call the function DFS, and instead of the node, which is the root, we'd set node.left, and then the right would be the exact same thing, except place this with this. So now this is the left subtree, this is the right subtree, and to find the maximum height, basically if you guys remember, the maximum height is going to be 1 plus max of left comma right, and that's what we're going to be returning. We're going to be returning the height of the tree. So this is the code just to find the height of the tree, if you guys remember. We can go back to the coding tutorial, the whiteboard, to see how this works. Basically, we have at this point it's getting kind of messy. I'm just gonna undo a bunch. Actually, I'll probably not spend too much time on this logic, but you have a left subtree, right subtree. This left subtree has a height of 2, this right subtree has a height of 1. So since we're trying to find the max one, we only take into consideration the height of the left subtree, and then that's that tree. It does the same recursive function where it finds this one and this one. The node becomes 0 here, but then you add 1 because the height of the maximum is 1, and then you add another 1 here. So the height of this entire thing ends up becoming 3, basically. So the height of this entire tree is calculated to be 3, but that's not exactly what we want. What we care about is the maximum sum of the left and right subtrees. And how do we do that? Simply, you see this max diameter function we have? We're going to continuously set it to be the maximum value of itself. Either we already have the max diameter, so we don't have to change it. Otherwise, if we get a bigger value in the left and right subtrees, we're going to be doing left plus right. And that's simply how it works. The left plus right calculates the height of the left subtree added to the height of the right subtree, and then compare it to see if it's bigger than the other max diameter. It starts out at 0, so it could obviously get bigger than 0. But once it hits a value, it checks to see if that value is the biggest number we have. Otherwise, we'll the maximum diameter has to be a different sum of the left subtree and a right subtree. And yeah, that's essentially it for the recursive function. All we gotta do now is run it here. So we're gonna be running it on the root, and then sorry, not def, DFS of the root, and then we're going to be returning max diameter. And that's essentially it. Now let's test our code. So for example, I'm going to paste this. This is the a test solution right here. It's a little bit different than what we're gonna be doing. So yeah, basically here we have the tree that we just made in the coding thing, where 1, 2, 3, 4, 5. The output is expected to be 3 because it goes from here to here. That's 1, 2, 3. Well, it's counting the edges specifically. So 1, 2, 3. That's the maximum diameter. And if we coded our function right, we should see an output of 3. So let's save the code, run it. Cannot access the variable max diameter. Oh, that's, I think the reason being we didn't input this into the place. So a quick way we can do this is we're going to put the word self in our main function here, and then we can have this be self dot max diameter. And what that will do is it'll make it as a global variable, not exactly a global variable, but a variable that everything inside this function up here can essentially refer to. So if we have self.max diameter here, we just put in self.max diameter here and here too. And then we're going to be returning self.max diameter. And if I did everything right, shoot. Give me a second, guys. Self is not defined. That means the okay, I think the way we're going to be doing this is we're going to be having it have a class. We're just going to call this the class of solution, and this is how we can access the class variables. So now when we do this, the self is referring to the class. Next we can essentially that entire thing, we're going to be saying, so we have to make the class object here. This is a little bit unnecessary, but I'm a little bit lazy, so we're just going to be doing this sol dot diameter of a binary tree, and then we don't need the self variable, we can just have the root. Honestly, it probably would have worked even without making the class. I should have just deleted the self thing here, but in any case, now that we finally run the code, we get the final output as 3. So yeah, that's essentially the logic of how this code essentially works. Pretty straightforward. There were some hiccups at the end, mostly related to some Python syntax that I had to clear up. There's probably an easier way to do it without involving this whole thing. But yeah, hopefully the logic was clear on how you'd figure out the height of the left subtree and then the right subtree, and add them together and find the maximum of constantly updating a max diameter variable to see the max value of those two heights. So yeah, hopefully you guys understood the solution, and I'll see you guys next time. Bye bye.